Imagine you have two coins, not just any coins. These are special connected coins. You and a friend stand together. You don't look at the coins. You just put each one in a separate sealed box. You give one box to your friend. Then your friend gets on a spaceship and travels to the other side of the galaxy. Years go by. One day, you decide to open your box. You look at your coin. It's heads. The very instant you see that it's heads, you know something with absolute certainty. You know that if your friend on the other side of the galaxy opens their box, they will find a coin showing tails. There is no doubt, it's guaranteed. Now you might think, so what? Maybe one was always heads and one was always tails. When you put them in the boxes, one was set to be heads, the other tails. Opening the box just revealed what was already there. That sounds logical. It's how our world works. If I have a pair of gloves and I put one in each of two boxes, opening one box to find the left glove means I instantly know the other box contains the right glove. The information was always there, hidden. But that's not what's happening with the quantum coins. The crazy part, the part that baffled the greatest minds in physics, is that until you opened your box, your coin wasn't heads or tails. Well, it was both. At the same time, it was in a fuzzy, undecided state. The same was true for your friend's coin. But the moment you looked, your coin was forced to choose a side. And in that exact same instant, no matter how far away, the other coin was forced to choose the opposite side. This is quantum entanglement. It's a connection between two or more quantum particles, like electrons or photons. Once they become entangled, they are linked in a profound way. They behave as a single system, no matter how far apart they are. What happens to one instantly affects the other. There is no time delay. It's not a signal that travels from one to the other. The connection is instantaneous. This is what Albert Einstein famously called spooky action at a distance. He hated it. It seemed to violate the rules of the universe as he understood them. To him, nothing could travel faster than the speed of light. The idea that measuring a particle here could instantly influence another particle light years away felt like cheating. It felt like magic, not science. He was convinced there had to be a simpler, more sensible explanation. He believed the information, like with the gloves, must have been there all along. He thought there were hidden variables, secret instructions that the particles carried with them from the moment they were created, telling them how to behave when measured. For decades, this was a debate between the giants of physics. Einstein and his camp argued for a predictable, logical universe with hidden rules. Niels Bohr and his followers argued that the universe was fundamentally weird and probabilistic. They claimed there were no hidden instructions. The particles really were in an undecided state until the moment of measurement. It was a philosophical argument, a deep disagreement about the very nature of reality. There was no way to prove who was right. Then, in the 1960s, a physicist named John Bell came along. He did something brilliant. He found a way to turn the philosophical debate into a real, testable experiment. He came up with a mathematical theorem, now called Bell's theorem. It's a bit complicated, but the core idea is simple. He figured out that if Einstein's hidden variables were real, then the results of a certain type of experiment would have to fall within a specific range. There would be a limit to how strongly the particles could be correlated, but if the weirdness of quantum mechanics was real, the correlations would be stronger. They would break that limit. Bell's theorem was like a set of rules for a game. If the universe plays by Einstein's rules, local realism, it can only score so many points. If it plays by quantum mechanics rules, it can score more. All that was left was to run the experiment and see what score the universe got. It took a while to develop technology precise enough to do it, but starting in the 1970s and 1980s, physicists like John Clauser and Elaine Aspect performed the experiments. They created pairs of entangled photons and sent them in opposite directions. They measured their properties, like their polarization. And every single time, the results were clear. The universe broke Einstein's rules. The correlations were stronger than any hidden variables theory could explain. The universe scored too many points. Einstein, it turned out, was wrong about this. The spooky action was real. Bohr was right. The universe, at its most fundamental level, is deeply strange and interconnected in a way that defies our everyday intuition. There are no hidden instructions. The act of measuring one particle really does instantly affect its entangled partner, wherever it may be. So how does this actually work? Let's move from coins to something more real, like electrons. Electrons have a quantum property called spin. You can think of it like the electron as a tiny spinning top. It can be spin up or spin down, like the coin being heads or tails. Before you measure it, an electron is in a state of superposition. It's not spin up or spin down, it's in a probabilistic cloud of both possibilities at once. It's only when you perform a measurement that its state collapses into one definite answer, either up or down. Now, imagine you create two electrons in a special way so that they become entangled. Their total spin must be zero. This means if one is spin up, the other must be spin down. Always. They are now a single system described by one unified mathematical entity called a wave function. You separate these two electrons, you send one to New York and one to Tokyo. In New York, a scientist measures her electron. The moment she does, its fuzzy state of superposition collapses. Let's say it collapses into spin-up. Instantly, the wave function for the entire system changes. The electron in Tokyo, which was also in a fuzzy state, immediately collapses into a definite state of spin-down. The scientist in Tokyo, upon measuring her electron, will find it is spin-down. This will happen every single time. The correlation is perfect. The key thing to understand is that the scientist in New York could not control the outcome. She couldn't decide to make her electron spin up. The result was random. It had a 50% chance of being up and a 50% chance of being down. Because she can't control her result, she can't use this to send a message. This is a huge point of confusion. People often hear about this instantaneous connection and think it means we can communicate faster than light. But we can't. Let's imagine the scientists in New York and Tokyo try to use entanglement to send a message. The scientist in New York, Alice, wants to send the message 1 to the scientist in Tokyo, Bob. They agree beforehand that spin up means 1 and spin down means 0. Alice gets her entangled electron. She wants to send a 1, so she needs to make her electron spin up, but she can't. She can only measure it. The outcome is random. She might get spin up or she might get spin down. She has no control. Let's say she gets lucky and measures spin up. In that instant, she knows Bob's electron in Tokyo is now spin down. But Bob doesn't know that. All Bob can do is measure his electron. He finds it's spin down. So what? To him, it was just a random result. He had no way of knowing if Alice had even made her measurement yet. The only way for them to confirm the correlation, to see that her up was linked to his down, is for Alice to call Bob on the phone or send some other classical, light-speed limited signal and say, "Hey, I just measured up." Only then can they compare their notes and see the spooky connection in action. So, entanglement doesn't allow for faster-than-light communication. It doesn't violate causality. It's a connection, a correlation, but not a communication channel. The spookiness is in the perfect instantaneous correlation between random events, not in the transmission of information. It's as if the universe enforces the correlation behind the scenes without sending a message. This non-local connection challenges our most basic ideas about space. We think of two objects as separate because there is distance between them. But for two entangled particles, that distance seems to be irrelevant. In a quantum sense, they are still touching. They are still part of the same system. This suggests that our human-scale perception of space and separation might not be the full story at the fundamental level of reality. The universe might be interconnected in ways we are only just beginning to grasp. For a long time, quantum entanglement was seen as a strange quirk of physics, a curiosity for philosophers and theorists to ponder. But in recent decades, we've started to figure out how to harness this spookiness for powerful new technologies. The most famous of these is quantum computing. A normal computer works with bits. A bit is a switch that can be either a 0 or a 1. A quantum computer works with qubits. A qubit, thanks to superposition, can be a 0, a 1, or both at the same time. This alone is a huge leap. But the real power comes when you entangle qubits. If you have two entangled qubits, they are linked. The state of one is tied to the state of the other. If you have 3 or 4 or 1,000, they can all be linked together in a complex web of entanglement. They act as one massive, unified computational system. When you perform an operation on one qubit, you are, in a sense, performing it on all of them simultaneously. This allows a quantum computer to explore a huge number of possibilities at once. For certain types of problems, like breaking modern encryption or discovering new medicines by simulating molecules, a quantum computer could be exponentially more powerful than any classical computer we could ever build. Entanglement is the resource that makes this incredible parallel processing possible. Another major application is quantum cryptography. Security today relies on mathematical problems that are very hard for classical computers to solve. But a powerful quantum computer could potentially break many of these codes, so we need a new way to secure our communications. Entanglement offers a solution. You can use entangled particles like photons to create a secret key for encrypting messages. Alice and Bob share pairs of entangled photons. They each measure their photons according to some randomly chosen settings. Afterward, they talk over a normal channel, like the phone, and compare their settings but not their results. This allows them to figure out which of their measurements are correlated and use those results to build a shared secret key. Here's the brilliant part. If an eavesdropper, Eve, tries to intercept the photons and measure them to learn the key, her act of measurement will disturb the quantum system. Remember, measuring a quantum particle forces it to collapse its state. This act of snooping will disrupt the delicate entanglement between Alice's and Bob's photons. When Alice and Bob later compare a sample of their data, they will find that the perfect correlations are gone. They will see errors and inconsistencies. They will know with certainty that someone was listening in. The very act of eavesdropping is guaranteed to be detected. Quantum physics itself provides the security. Entanglement is also being used to create incredibly precise sensors, things like quantum clocks that are so accurate they wouldn't lose a second in the entire age of the universe, or medical imaging devices that can see biological processes at a level of detail never before possible. By linking particles together, we can make them more sensitive to tiny changes in their environment, like a gravitational field or a magnetic field. Despite these practical applications, the fundamental mystery of entanglement remains. What is this connection? How does the universe enforce it? Physicists have several different ways of thinking about it, known as interpretations of quantum mechanics. The oldest and most common is the Copenhagen interpretation, developed by Niels Bohr and his colleagues. It basically says, don't ask what's happening behind the scenes. The math works. The predictions are accurate. The wave function is just a tool for calculating probabilities. When you make a measurement, the wave function collapses, and that's all there is to it. It's a very practical, shut up and calculate approach. It doesn't try to explain the why of the spooky connection, it just accepts it as a fundamental feature of nature. Then there is the many worlds interpretation. This one is more mind-bending. It suggests that the wave function never collapses. When you measure an entangled electron and find it to be spin up, the universe splits. In one universe, you got spin up, and its partner is now spin down. In another parallel universe, you got spin down, and its partner is now spin up. Every possible outcome of every quantum event happens, each in its own separate branch of reality. In this view, there's no spooky action at a distance. The correlation is built into the branching structure of all these universes. The particles aren't sending signals to each other, they're just following the rules of their shared existence across the multiverse. There are other interpretations too, like pilot wave theory, which suggests there are hidden variables, but they are non-local. This means there are hidden instructions, but they can influence things instantly over vast distances, so it's still spooky. No one knows which interpretation is correct, it's possible we can never know, they all make the same testable predictions. The math is the same. Their differences lie in the stories they tell us about what reality is, really like when we are not looking. Choosing between them is, for now, more a matter of philosophical taste than scientific proof. What we do know, thanks to John Bell and the experiments that followed, is that our everyday intuition is a poor guide to the fundamental workings of the universe. Reality is not local in the way Einstein hoped it would be. Things are not as separate as they seem. This can be a difficult idea to accept. We are built to experience the world in a classical way. A ball is here, or it is there. It can't be in both places. An action here has a delayed effect over there, an effect that can't travel faster than light. These seem like non-negotiable rules, yet quantum mechanics tells us that these rules are just approximations that work well for large objects like us. The underlying reality is a web of probabilities and instantaneous connections. The story of entanglement is a story about how science works. It started with a puzzle, a weird prediction from a new theory. It led to a deep philosophical debate between two of the greatest minds in history. It took a flash of insight from another brilliant physicist to figure out how to test the idea. And it required decades of technological progress to finally perform the experiment and get a definitive answer. And the answer is that the universe is spookier than we imagined. The connection between two entangled particles is not a trick. It's not a metaphor. It is a real, fundamental feature of our world. Two particles, born together, can be separated by the width of a galaxy and still remain, in a profound and mysterious sense, a single entity. What you do to one, you do to the other. Instantly. It's a reminder that there are still deep, fundamental questions about the nature of reality that we don't have answers to. What is space? What is time? What does it mean for two things to be separate? Quantum entanglement doesn't just give us new technologies, it forces us to confront these questions. It challenges the very foundation of our perception, and it shows us that even in our modern, technological age, the universe still holds an immense capacity for wonder, for mystery, and for genuine, honest-to-goodness spookiness.